Hello everyone. In today's class we are going to discuss about Vitali covering lemma. Now, first of all, what is meant by Vitali covering? Suppose zeta is a collection of intervals and zeta covers a set E in the sense of Vitali if for every epsilon greater than 0 and for any x belongs to E, there exists an interval in zeta, say I, which contains x and length of that interval is less than epsilon. Now let us see what is Vitali covering lemma. Vitali covering lemma says, suppose E is a set of finite outer measure, that is M star E is finite, and zeta is a collection of all intervals which covers E in the sense of Vitali. That means if you choose an point in E, then that point will be present in one of the interval, and that interval will have a length which is less than epsilon. Then for given epsilon greater than 0, there is a finite disjoint collection of intervals of zeta such that the outer measure of E minus this union is less than epsilon. Now in fact, to prove this, we prove for the lemma in the case of interval in zeta which are closed, because if you consider open interval, we'll consider the closure of that, so that this lemma holds. And observe that the endpoints of this I1, I2, etc. up to In as measure 0. Remember, I1, I2, etc. up to In as measure 0. Now, suppose O is an open set of finite measure containing E. And since zeta is a Vitali covering of E, we may assume that each I of zeta is contained in O. And now we'll choose a sequence of disjoint intervals, because we need a sequence of disjoint intervals of zeta by induction as follows. Let us assume I1 is an interval in zeta, and suppose these interval I1, I2, etc. up to In are already chosen. Then we can choose other intervals, those intervals which do not meet any of these, and for them the maximum length will be, that is supremum, will be Kn. And remember, each of the interval of zeta is present in O. Therefore, suppose I is an interval of zeta, then I is also contained in O. And you know that if all these intervals are present in O, then, and you know that those intervals which do not meet any of these interval, their length is Kn. So Kn will be obviously less than or equal to M star O. And O is a open set of finite measure. Therefore, the Lebesgue outer measure of this is finite. Now, if E is completely contained in this, then there is nothing to prove. So assume that E is not completely contained in union I from 1 to N, I. Then there exists at least one interval, In plus 1, for which if your x is present in E, then x is in In plus 1 and length of this will be less than epsilon by the Vitali covering definition. Then we can find this interval In plus 1 in zeta which do not meet any of these interval. And we know that those intervals which do not meet this, their maximum lengths will be Kn. And assume that length of this In plus 1 is greater than Kn by 2. So, in this way we have constructed the sequence of disjoint intervals of zeta, and all of these are present in O. Therefore, their union is also present in O. And what is the Lebesgue outer measure of this? m star of this is less than or equal to m star O. But m star of this union is nothing but summation n from 1 to infinity m star of in. But the Lebesgue measure of an interval is its length. Therefore, this becomes summation n from 1 to infinity length of in, which is less than or equal to m star O. And since your m star O is finite, the Lebesgue, so this summation has to be finite. Therefore, for given epsilon greater than 0, because this series, which is converging to 0, therefore we are having an integer n such that summation n plus 1 to infinity length of in is less than some arbitrary number, say epsilon by 5. And let us assume that A is collection of all elements E minus this union. Then the lemma will be established if we show m star A is less than epsilon. Let us say X is an element in A. Then X is present in E, but X is not present in any of this. And remember, we are proving the lemma for the intervals which are closed. So finite union of a closed set is closed. Therefore, this set is closed. And X is not present in this closed set. And remember, your zeta covers E. And every element of A is present in E. Therefore, there must exist an interval I in zeta which contains X. And since X is not present in this, I cannot meet this interval. Now, you should note that we have defined while defining this sequence that those intervals which do not meet any of these can have maximum length kn. So length of I can be at most kn. But remember, your length of in plus 1 is greater than kn by 2. So what is twice the length of in plus 1? It is 2 times kn by greater than 2 times kn by 2, or 2 get cancels. Therefore, twice the length of in plus 1 is greater than kn. So that is what we have written. Length of in is less than or equal to kn into twice the length of in plus 1. And remember, the limit of in as n tends to infinity is 0. Therefore, since this is tending to 0, this interval I has to meet at least one of the interval. It does not intersect with I1, I2, etc. up to in. But it may meet any of the interval because you know your length of I is less than or equal to kn. And limit of this is 0. Therefore, I has to meet one of the interval, say in plus 1, I capital N plus 1, etc. Not any of the interval I1 to in. It has to meet one of them. Thus, we have a integer n such that n is greater than n and length of I is less than or equal to, because you should note that those intervals which do not meet these can have at most length kn. Since it is meeting one of the interval in, must be less than or equal to, its length must be less than kn. So we are assuming it is less than or equal to kn minus 1, which is less than twice the length of in. Now, since x is in I and I has a point in common in in, it follows from this that the distance from x to the midpoint of in can be at most length of I plus half the length of in. But length of I is less than 2 times in. So this is less than 2 times in plus half the length of in. 2 into 2 plus 1, which is 5 by 2 length of in. So the distance from x to the midpoint of in can be at most maximum this. Otherwise, the length will be kn. But we knew that the length cannot be kn. It can be at most kn minus 1. Therefore, length of x to the midpoint of in is at most this, because in and I are having a point in common. Thus, x belongs to some interval, say jn, having the same midpoint as in and 5 times the length. That is, jn and in having the same midpoint, and x belongs to jn, and the length of jn is 5 times length of in. Remember, your x is coming from a and x is present in jn, therefore x is present in this union where n runs from n plus 1 to infinity. And what is the m star of a? M star a is less than or equal to m star of this union. Since these jn's are disjoint, m star of this becomes summation n from n plus 1 to infinity m star of jn. But since jn's are intervals, the Lebesgue outer measure of intervals becomes length. So n is equal to n plus 1 to infinity length of jn. And since length of jn is 5 times the length of in, so 5 times length of in, and we knew that summation n plus 1 to infinity length of in is less than epsilon by 5. If you replace it, we'll get epsilon. So we have proved m star of a is less than epsilon, where a is e minus union n from 1 to capital N in. And this completes the proof. And given exercise on Vitali lemma, you just work it out. Thank you.